section 5.1 is called Perpendicular and Angle Bisectors, and you guys should already have a rough idea of what those are because we just did constructions on them, right? We did a perpendicular bisector of a segment, and we drew an angle, and we bisected it using the safety-based compass, okay? So some vocabulary words that are going to come up in this chapter are the word equidistant, and not as often, but a word you might see is a word called locus. So equidistant has equa in it. Equa is sort of sounds like equal, right? So equidistant is just going to be a point that is the same distance from two or more objects. In geometry, those objects are usually a line, a point, okay? And then a locus, you won't see this word as often, but it's going to be a set of points that satisfies a condition. All right. So the first thing we're going to talk about is something called the Perpendicular Bisector Theorem. Perpendicular Bisector Theorem. I'm going to read it to you and then we're going to draw a little picture to help explain it. All right, so here's what it says. It says, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay? So if you remember when we were drawing our constructions, we started with a segment. I think we even called it A, B, right? Then we used our compass and we made an arc here and an arc down here and another arc from B up here and down here. And we ended up drawing in what's called the perpendicular bisector, okay? It's perpendicular, so we're going to put that little box, and it's the bisector, so this piece becomes congruent to this piece, okay? So this theorem says that any point on this perpendicular bisector is going to be equidistant from the two endpoints. So if I pick a random point on here, let's call this point right here C as in cat. I randomly picked a point. That point is going to be equidistant. So if I were to draw in a line from A to C and from B to C, they would be what we call equidistant. Equal. And in geometry, that ends up being congruent, right? So AC is going to end up being congruent to BC. And you can kind of even see, just from looking at it, that that's true, okay? It could be any point. So I picked one randomly up here, but if I had picked one randomly down here, call this one D as in dog, it's also going to be equidistant. So if I dash in this line segment and this line segment, those two are also congruent. So we're going to say that AD is congruent to BD. How many more random points could I pick on this perpendicular bisector? How many more random points could I put on here? As many as we wanted. We could keep going, right? There's an infinite amount of points on this line that are all going to be equidistant from those two endpoints, okay? The other thing that you also need to know is that the converse of this theorem is true, okay? The converse says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector. So if AC is congruent to BC, then that point is somewhere on that perpendicular bisector. Okay? So let's look at an example that you might see on your assignment. This is called example number 1. We're going to have segment ML. We're going to pretend like we bisected it with a safety-based compass and it's perfect. And we end up with this beautiful perpendicular bisector. So we're going to put a little box to show that it's perpendicular. We're going to put 2 tick marks to show that it bisects it. And then we're going to randomly pick a point somewhere on that perpendicular bisector. We'll put it up here, but it could just as easily be down here. We'll call it N as in Nancy. Okay? If we connect M to N and L to N, they're going to be equidistant. And if the problem was super easy and said that MN was 5 inches, how long would LN be? 5 inches. But instead of just being an easy number, it's going to be an algebraic expression. It's going to be 3x plus 9, and it's going to be 7x minus 17. So we're going to take those 2 algebraic expressions and we're going to put a what in between them? Equal sign. So we're going to say 3x plus 9 equals 7x minus 17. And then we pretend like we're back in Algebra 1 and we want to get the x by itself. Okay, so first of all, we need to subtract 7x from both sides. In the same step, I'm also going to subtract 9 from both sides. These are opposites and these are opposites. So on the left, we have 3x minus 7x, which is 4x. On the right side of the equal sign, we have negative 17 minus 9 more. That gets us to what? Negative what? 26.
Isn't it negative 4?
Yes, thank you for catching that negative sign. Okay, so we have negative 4x and negative 26. Then we divide both sides by negative 4. So x is equal to 6.5. Or you can write 6.5 if you like fractions. Okay, so if the problem asks you to solve for x, you're done. But sometimes instead of asking you just to solve for x, it'll say, what is the length of MN? Or it'll say, what is the length of LN? Would it matter which one you plug the x back in for? No, because they're equal. They're equidistant. They're congruent. So we're just going to plug it into whichever one looks easier. I think this one looks slightly easier. So I'm going to say 3 times 6.5 plus 9. Punch it in my calculator, hit the equal sign, and I get 28.5, which means that LN is what? 28.5. I'm going to move this up. You'll see it in just a second. There it is. All right, so that was the perpendicular bisector theorem. We have one more, which is the angle bisector theorem. So the other day when we were doing constructions, we drew an angle. We took our safety-based compass, we made an arc, and then from each of those 2 intersection points, we made a longer arc out in no man's land, right, and made them intersect. That created a point where we could draw a third ray through, right? You guys remember doing that in your pink paper? All right, so here's what the angle bisector theorem says. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle. Okay? So guess what we're going to draw first? That would be an angle. Since it's called the angle bisector theorem, we're going to start by drawing an angle. We'll make the vertex P as in Paul. We're going to pretend like we're using our safety-based compass, and we make an arc, and then we make 2 arcs further out, and we end up with this beautiful angle bisector. So this theorem says that if a point is on that angle bisector, so anywhere along this angle bisector, you're going to put a random point. I'm going to pick right there. Okay? This theorem says that that point is equidistant from the 2 sides of the angle. So from here to here, we'll call this point A, and from here to here, we'll call this point B. Okay? They're equidistant. That means they end up being the same distance, and this is point C as in cat. So AC is going to be congruent to BC. They're also going to be perpendicular. So we're going to put a little box right here, and we're going to put a little box right here. All right? So let's look and see an example that you're probably going to see on your assignment. We'll call this example number 2. And we're going to need an angle. So we'll call the vertex K. We're going to pretend like we have an amazing compass. We draw our arcs. We get a beautiful angle bisector. We'll call that ray KM. And we'll put a point over here, call it J, a point over here, and call it L. Okay? So I'm going to tell you that angle JKM is 3A plus 20, and angle LKM is 2A plus 26. Of course, they have to throw algebra in there, right? If they had just said that this angle was 25, and what's that angle going to be? 25. What would the whole thing be? 50. What if they told you the whole thing is 120? What would this one be? 60. Okay, so if they're just using numbers, easy. It's either going to be the same, it's going to be double, or it's going to be half. Okay, but in this case, they give us these algebraic expressions. If these 2 angles end up being congruent because we perfectly bisect it, then we set them equal to each other. So I'm going to take the expression 3A plus 20, set it equal to 2A plus 26. And then I'm going to pretend like I'm in Algebra 1 class. So I'm going to subtract 2A from both sides, subtract 20 from both sides in the same step. These are opposites, these are opposites. So 3A minus 2A is 1A, and 26 minus 20 is 6. Okay? If they just want the variable, you stop there. But sometimes they're going to want you to plug it back in. So there's 3 different angles they could ask you about. They could ask you about angle JKM. They could ask you about angle LKM. Or they could ask you about angle JKL. So if you're not sure which one is which, then take your finger or your pencil and tap it out. Is it one of the 2 smaller ones, or is it the whole bigger one? Okay, so it's obviously going to be easier to start with one of the smaller ones. So I'm looking and saying, okay, that one looks a little bit easier, and that's LKM. So LKM, I'm going to say 2 times 6 plus 26. Punch it in my calculator, hit the equal sign. I get 38 degrees. Okay, so if this smaller angle is 38, what's this smaller angle going to be? 38 as well, and that one's JKM, which is